t-test reporting goes like this. I'm on the t-test portion right now. So, well, we haven't learned how to report chi-squares, but you always, when you do the reporting, you can definitely, and you should, report the degrees of freedom, all right, and the statistic of the t-test. So what is the statistic of the t-test? Is the t-value. That's why, it's usually called the t-test. Today we're going to learn about ANOVA, and that's the f-test. So the t will always be reported here with the degrees of freedom in parentheses. So the t statistics rounded to 2 decimal point. One other important and necessary value that you have to report is the significance level. So what is the p-value? Okay, and I'm going to show you there. But generally, there are only two tables that you have to report. One is the mean comparison, where you compare the mean of the two groups. For example, here is the group that never binge drink, that were never binge drinking, and the other one that was binge drinking one or more drinks. So in this case, that's the mean value. The n is the sample size for the groups, and then the standard deviation that you have to report always. Now the t-test is this. You can simplify. You know how big that, how long that table is, how wide, right? And it shows you the f-test for the equality of variance, the Levene's test, and because of that, you have to, based on that, you have to choose whether or not the equal variances were assumed or not assumed, and then choose the t-value. And you don't report the p-value here, just the t, okay? And if the p-value is significant, then you put an asterisk, one asterisk, next to the t-value. One asterisk is significant at the 0.05 level. Two asterisks are significant at the 0.01 level. If there are three, then it's significant at the 0.001 alpha. Okay, so that's how you report the t-value. You have to report the degrees of freedom, of course. And if it's significant, then you put the asterisk on the t-value that corresponds to the Levene's test of equal variances assumed or not assumed. Okay, that's what it means. The 3.93 here is the t-value for the equal variances assumed, and you already know that that's the t-value that you report because the f, or the f value in the Levene's test here is 0.165. I'm sorry, the p-value is 0.165, which is greater than 0.05. Therefore, you fail to reject the equal variances null hypothesis in the Levene's test. Therefore, you assume those variances to be equal. Therefore, you look at the first row. Now, in terms of how you would write that in the report, is basically this, that if the null hypothesis was rejected and you accepted the alternative hypothesis of finding a significant difference, then you would say that there was a significant effect for weight loss treatment. And then what you do is you put the t in parentheses, the degrees of freedom, and then equals to the t, right? And then comma, and then the p-value. The p is, here I should have probably put 3 asterisks over here, because if the p is smaller than 0.001, then that is definitely smaller than 0.01. Yeah, it's definitely smaller than 0.01, and even more smaller than 0.05. And you would say with those who exercised, in this case, the mean would be 3.25. Well, actually, this sample is not about those who exit. Oh yeah, this is student binging in college and those who exercise. Losing more weight than those who did not, mean 2.89. Okay, or if this was the number of drinks, then you would say that those who drunk, mean 3.25, lost more weight, or those who never binged, drunk. Well, hold on a second. This is about the losing weight. So this is not about the number of drinks, because those who never binged, they didn't have more drinks than those who binged. All right, so this is about those losing more weight. And so in this case, that's how you write it down. I could simplify this, and I said I will, and
I mean,
I would.
it makes sense.
But that's how you do the reporting. Before you say one more thing, in the book, okay, when you say the reporting the t-test, this is how you find out. I think this is section 10.10.1, reporting the t-test, and you say on average, participants given a cloak of invisibility engage in more acts of mischief, and then you would put the mean and the standard deviation here. Well, you can leave, I'm sorry, the standard error. You can also leave the standard error out here, okay, when you place the table in the report. Okay, so here we have the standard deviation. You can also put the standard error. That's fine, whichever that makes more sense, because if you know the standard deviation, you also would know the standard error. Or if you put the standard error, you also can compute the standard deviation. Because what is the standard error? Standard error is the standard deviation, this, divided by the square root of n. Okay, so and then those not given a cloak, so those who are given one and those who are not, and then this difference, you can leave the 90% out if you want, was not significant, but this is important. See, the t in parentheses, degrees of freedom, and then the p-value. Sometimes you can put the p-value as equal to, especially when the p-value is not smaller than 0.05, then you have to put the exact p-value, because that's greater than 0.05. But at other times you can put p-value smaller than 0.05. You don't have to put the whole number here. So either one of these, what you see in the textbook or what you see here, is fine. So that's all I have to say about that. Yeah, Javid, what were you saying?
No, that answered my question. I guess I was wanting a little more clarification, because I saw, like I said, the textbook was slightly different. Had a little more data, and then in previous class I've had, there was
right. There was this that I explained.
Yeah.
You're right. In APA style, generally you have to put as matter of being standard, the t degrees of freedom parentheses equals the value, and then the p-value, and also the mean. These are necessary. If you want to put more, just like in the book, you can, but generally in the APA style, I don't think that these have been there for a long time, like standard deviation or the standard error or the confidence interval or the 95%, right, confidence level. Okay, so that's that. Who also had a question? Who else?
That was me.
Okay, yes, go ahead, please.
So when you're doing the independent samples t-test and you look at the Laverne's section,
yes,
the F statistic, so if you fail to reject the null, do you still have to look at the bottom section of equal variances not assumed?
Okay, let me see if I have it here so that, okay. So if the Levene's test gives you a p-value that is greater than 0.05, correct?
Yes.
And then you fail to reject the null hypothesis of equal variances. So if you fail to reject the null hypothesis, if you fail to reject that equal variances are assumed, then that stands. Therefore, equal variances are assumed. And that is the indicator of which row to look at. Therefore, you look at the first row, the row on top, and then you go across to the right, and then you look at the p-value of the t-test, because this is the t-test. If you have a line here, okay, a horizontal line that would separate the Levene's test from the t-test, it'll be right here, okay? And so the Levene's test, this area right here, is only to show you where to look. Equal variance is assumed or equal variance is not assumed. If the Levene's test significance is greater than 0.05, then you look at the equal variances are assumed. If this p-value was smaller than 0.05, then you reject the hypothesis of equal variances, therefore equal variances are not assumed. And then you look at the second line. All right, so if it's greater, look at the first line. If it's smaller, look at the second. And then you look at the p-value. This is the most important p-value here, because this is the p-value of your initial hypothesis. Okay? Does it make sense? I think I had a PowerPoint that I showed last class.
Yeah, I saw the PowerPoint, but when I was reading the textbook, the author said that we generally look at the equal variances not assumed. So I was kind of confused about that.
Oh, why would he say that? Can you show me which page? I don't think I've encountered that.
Okay.
Then again, you know, this is a new textbook, so I have not read everything. Okay, this is it. So, oh no, yeah, this is it. Are you seeing this?
Yes, I see it.
Okay, so yeah, well, you don't automatically look at the equal variance is not assumed. No, you don't look at that. You have to, whether you see this upper p-value or this lower here, depends on what this significance of the Levene's is. If this is greater, then you look at the equal variances are assumed. So you go up here and you look at the 0.00. If it's smaller, in this case it's not, but if it's smaller, then you look at the bottom. Equal variances are not assumed. So this is kind of like a map, you know, whether you look at the bottom or the top significance depends on whether or not the significance for Levene's test is smaller or larger than 0.05. Now, like I said before, this could be 0.1 and it's fine, you know, but it depends on what you want to do. If it's a study that you're doing, then you're going to have to decide. You know, it's fine if you decide that the Levene's test is going to be tested at an alpha of 10%, you know, reference probability of 10%, which is 0.1. That's fine too, okay? Because generally these two p-values are not so different as you probably have seen, because the mean difference is the same, all right? What's different here is only the degrees of freedom. And the degrees of freedom do not change drastically here. And you know, the t-value is computed differently, but also, as you can see, is not so different, right? And if it's not so different, then the t-value is divided by the degrees of freedom is going to, or just the t-value and the degrees of freedom is going to give you an area of the normal curve, or if it's not normal because the equal variances are not assumed, a significance that is not so much different from each other. Okay, I'm just going to. All right, so.
Okay, thank you. I understand now.
You're welcome. Make sure really that this is one of the areas that you do understand, because it's going to be in the final. That's for sure. And
okay, he said on page 343. It's on page 343.
343. Cramming Sam.
Yes, there.
The independent convenience means. Okay. Well, says you should probably ignore. Maybe I wouldn't say that. I would recommend that you, and I would want to teach you the right way. So you don't do any shortcuts. Just know exactly what it means. If where was it? Here. Just know exactly what this means, you know, and know the map. I by nature I'm inquisitive, so I want to know, you know, and I like to solve puzzles. So this looks like a puzzle to me. Where do I look at? Look at the top or the bottom? Oh, I can't really know which one to look at right now, unless I understand what this means. So this is the key to the puzzle. All right, so this significance. If it's greater than 0.05, then just like in any hypothesis, that's evidence for the null hypothesis. And null hypothesis is always that things are equal, right? Or no relationship. If things are equal, in this case, what are things? In this case, in the Levene's test, things are equal variances, meaning variance of the groups. So if we have two groups, which we do, then do we assume that these two groups have equal variances, right? And we assume that the variances are equal between the groups in a null hypothesis. So if now we have a lot of evidence for this null hypothesis, we can't reject it. If we can't reject, then we do assume indeed that variances are equal. If we assume that variances are equal, then we look at the equal variances assumed row. If not, then variances are not assumed. Therefore, we look at the bottom line. Right? So I know that, you know, you haven't been presented with this thing before. It's only a few weeks that that you have to learn this. Okay, it's a puzzle that you might learn now and then forget after the class. Okay, but for this class and for the comms, I think that you do need to learn it. If you can't learn it, you know, by heart, just write it down somewhere, figure out a way, and that's why I created this sort of where did this other thing go? Right, the PowerPoint that PPTX that just shows you, moves around. Create the map yourself, and keep it ready for your assignments, right? For final exam, for the comps, and so on. There are always, ways how to figure this out. And that's why actually I told you before that the t-test is one of the most important and also one of the most difficult to understand. And this is the report that everybody kind of has a hard time understanding. But once you understand this, then ANOVA is so easy. And also the paired samples t-test is also easy because you don't have the Levene's test here. Okay. Also, I remember saying that where is it? Right, use the Excel to conduct the two samples t-test. Why? Because Excel does not have, a one overarching test like SPSS. In Excel, you have to do one test first. You have to do the Levene's test first, and then based on that, you either do the equal variances assumed or not. I don't think I have this open. I could show you quickly, but you can always use in Excel, right? I don't think I can. If I can just go here very quickly, let me actually show you very quickly what's going on here. So, hello guys. In this podcast, I will show you how to do the independent samples t-test and the dependent samples t-test in Excel. Here's the idea that I have. I want to take my vacation, but this is about, these are two groups, right? These are two places, and these are the low temperatures in January. So there are 31 measurements, one for each day, and I want to figure out which one, if there's any difference in the mean temperature in January, and if there is, which one is higher on average. And that's when I decided to go, on vacation, and I'm gonna go where it's hot, right, or hotter. So that's why I want to do this t-test here. All right, and this is an independent samples t-test because Cancun and Punta Cana are two independent entities. It's not a before-after measurement. It's two measurements of two different cities for the same period. Okay, so what I just want to go further. Right, so I don't know how many of you have watched this. Okay, if any had watched it, I would commend you for the torture going through all of these videos. This is 17 minutes, but I have some longer videos. So in Excel, you have to do another test before you do the t-test. And that test that you do before is called the f-test, right? Or the test for homogeneity of variances, or the test where you can find out if you assume equal variances or not. Okay. Because depending on that particular result, you have to do the t-test. The t-test that assumes equal variances or the t-test that does not assume equal variances. So let's start with the f-test first. You have to go to the data tab, right, and then find the data analysis toolpack button. If you don't have that, you have to go to the file menu, right, find Excel options, then go to add-ins. Very quick. And in add-ins, go down here where you see manage, click go, and then select analysis toolpack, check that box, click OK, wait a minute or so, and then analysis toolpack would be right here in the data tab. So click on the data analysis. When you do that, right, you have to go to the f-test for two samples for variances. So click on that particular test, click OK, and now you would see probably two empty spaces. So the first range would be the first variable, and the second range would be the second variable data. One other thing that is very important in Excel is that the variable one range should have the largest variance. and the variable 2 range should have a smaller variance, right? Because the f-test is actually the ratio of variable 1 over variable 2. So that's correct, and you don't know which one of these variables has the larger variance until you do a simple calculation, right? Which is the standard deviation square. You can get the standard deviation for the first group, standard deviation for the second group, and then you compare which one is the larger, and that would be the larger variance, because variance is the standard deviation square. And then you can put the larger variance variable up here and the smaller one down here. You would probably do that. I already did that here, but I just said that I wouldn't know, so I'm just writing it down or selecting one over the other. In this movie. But at the same time, you can also check the label, so you can see the group name, Cancun or Punta Cana, and then you can figure that out. But I just want the output to be right here in this page. Therefore, here. E5 would be the place where I want the output. So I click OK, and now I have the f-test for variances. Okay, so the f is greater than 1. The gut feeling was correct, because the variance of variable 1 is greater than variance for variable 2, right? And the p, or probability value, is a scientific notation. Therefore, I need to change that to a number. That is very small. Is 0.00. I want to increase decimals to just see what's going on here, right? Right, the p here. Look at that. That is such a small probability. Right, smaller than 0.05, we reject the null hypothesis that we should assume equal variances. Therefore, we do not assume equal variances. Equal variances are not assumed for this t-test. Okay, so now we know which t-test to do. So we go into this other cell, go to the data, go to data analysis, and now we have to perform the t-test. See how many t-tests are here? One that we want to perform is this one right here, is t-test 2 sample. Assuming unequal variances, right? Because that's why we did the p-value over here. Okay, so you would imagine, what happens next. But the reason why there are 2 t-tests, one for equal variances and the other one for unequal variances, are because they use different formulas. Namely, the degrees of freedom are different, are calculated differently. And at the same time, the t-test, has a different formula, right? And that's why here, right, you have a significance of p-value for equal variances and a p-value for unequal variances, which SPSS does in one consolidated test. In Excel, you can't do that because you need to figure out which test to perform, which t-test to perform, the one with equal variances or the one without variances, right? In my opinion, if I wanted to teach students better, I would just show the Excel version, because in Excel you have to really understand, the f-test first, and then based on that f-test to choose which one to do. SPSS sort of, assumes that everybody who uses SPSS would know this, and that's why it gives you only one test. So that's the difference. You have one test here to simplify, the way that we do we conduct the test, but the catch is that you have to know how to interpret the Levene's test. So you see the difference. In Excel, you understand more, you know how to do the f-test, but you have a lot more work because you have to do two tests. Here you do one test, assuming that you know how to interpret the Levene's test. Okay, so basically that's what lies behind the scenes in the t-test. So this is for interpretation. I wanted to let you guys do one, assuming that you have SPSS open. I wanted to want you to do an exercise. The exercise would be open up GSS 2008 Student Edition. You know, that is found in Blackboard. You go to Datasets SPSS Excel. And once you go there, you go to the folder GSS Datasets. In GSS Datasets, you go to 2008 GSS files. I have to compile more accurate GSS data. And then you open up GSS 2008, the Student Edition. Okay, in Student Edition, go ahead, I'll wait. You have a lot of variables that have yes or no. Okay. And a lot of those have to do with abortion for any reason, abortion for defect, abortion. And so if you want to figure out what they mean, you have to go to the label. So abortion if a woman wants for any reason, strong change or serious defect in at birth, health seriously endangered, married, no more children, low income, can afford, pregnant as a result of rape. These are very good questions, you know, and we're going to do some of these when we talk about the cross tabulation and at the same time chi-square, because a chi-square tabulation will need variables that are categorical in nature, right? So I want you to do a t-test that measures, you know, if there's any significant difference between yes or no okay, in the age between those who own a gun and those who don't own a gun. So the null hypothesis would be that there is no significant difference in the age of those who own a gun versus those who don't own a gun. And the alternative hypothesis would be that there is a significant difference. So test that at 5% alpha level. So go ahead and I'll wait. And then I'll show you how to do how you can do it, and then you can just compare. Yeah, Victoria, I'll see if I can save that as a PPTX, not PPTS, which is just a show, PowerPoint show. I think that's how I initially created it, to be as a show, so that it can show you where to go and sort of like direct you where to look. That's fine, don't worry. Okay, so did you finish? And if you did, can you tell me what did you find? If you haven't finished yet, okay, I'll give you a few more minutes. I really like this data set because it gives you sort of an adventure in not only in criminal justice, but also in social research, owning a gun, or views on gun ownership. I'll do a couple right now, and then I'll move on to ANOVA. Just make sure that I'm recording this. Am I recording this? I think I am. My settings. Yeah, I am. Okay, so you can go back and check it out. Anybody finished? If you don't have to speak, just write in a chat. Yes, no. I'll move the chat away so that not everybody can see your chat if you don't want to. Well, anyway, they can see it because it's what you call, it's not a private chat. All right, so if you're not able to do this by now, I think there can be a slight problem. Yes, Chantal.
I finished.
Okay. Right. What did you find?
We failed to reject the F test in the first row.
The F test. Yes, that's correct. Okay, I see that. Let's move on from the F test and see what do we do with the general hypothesis. So the null hypothesis was that there is no significant difference in the age of respondent between those who have a gun and those who don't own a gun in the home, right? So generally, the mean age would be equal. No difference between the age of those who have a gun and those who don't. So what was the mean age of those who have a gun at home?
Was it 47.4?
No, the variable is have gun in home, right? Have gun in home. Have gun in home. Right here, own gun. Did you use that?
Oh no, I did favor or oppose gun, and then the age.
Okay, you can change that.
Okay, I'll change it.
Okay, guys, have you? So I have 1, 2, 3, 4, 5, 6, 7. Javid just left. So eight students. So guys, everybody else, did you have a chance to do it? Again, have gun in home is yes, no, right? So you have to make sure that yes and no are labels, right? But the values are 1 and 2. Okay, that's very important in distinguishing or defining the independent variable in the t-test. Are you struggling with that? Oh, okay. Opening SPSS. All right, maybe, yeah, maybe you guys have problems with opening SPSS. That's a different thing. Okay. Yes, Chantal.
Okay, so I fixed it. 200 people have a gun at home. If I'm reading it right.
Yeah.
Okay.
Yeah. What is the mean age of those who have a gun at home?
54.05.
That's correct. That's it. All right, I'll show. Also, the data set is 2008 student edition, student version, I think. Let me see. Student edition, yeah. GSS, I'm sorry, GSS 2008 student edition.sav is right here on the screen. All right, good. So, correct. Yes, Jonathan. All right, so let me show you how to do it quickly. You already did. So what is the p-value of the t-test?
Is less than 0.05.
That's correct. All right, so the idea is that we have this data set. When I look at this data set, I just don't know which test to do before and first, because there's so many things that I want to know. Okay, so right now I just want to know whether or not older people buy. Oh, and by the way, right now this moment I'm going to show you a circuit which is going to help you in the final, and that is a trick, because in life, when you go and do statistics, not everybody is going to give you a null hypothesis or an alternative hypothesis to go and test, because that's kind of easy. But a lot of people, might give you a question like this that says, test whether or not older people own more guns than younger people. So how would you go about doing that? It's the same thing as the hypothesis that I just gave you. Write that down, okay? Write it down right now, because I'm going to tell you the same thing, but in a different way. Before I told you that, okay, there's no difference in age between those who have a gun, own a gun, and those who don't. But right now, I can just tell you a different way, and I just said that test the hypothesis that younger people own less guns than older people. So how would you go about doing that now? Younger people, older people, what to do? Some of you might want to go to the variable age and compute that and put a cutoff point, I don't know, at about 45, and saying that, okay, less than 45, younger people, 45 or older people. Why? Because you would not think that in a t-test, there's one categorical variable and one numerical variable. Which one is the categorical variable here? Categorical variable right here is have gun in home, right? Own gun. Where is it? Right here. All right, pay attention here, because this is very important. Have gun in home is going to be your independent variable, and it has two groups, yes or no. Now, inapplicable, refuse, don't know, not applicable, they are not valid answers, right? Yes and no are valid answers. Yes and no constitute two groups. Two groups is very perfect for t-test. So now I'm going to ask you in the final, all right, this is a t-test. Test whether or not, well, imagine that I was going to ask you this question. Test the hypothesis that younger people own more guns than older people, or older people own more guns than younger people. So now you have variable age, older, younger, and you have own gun. Own gun is the categorical variable, so that has to be the independent variable. And age is going to be the dependent variable. All right, so don't go and create a new variable based on age that you make it from numerical variable into a categorical variable, because now you're going to have two categorical variables. Own gun is going to be categorical because you can't make that numerical. You know, as you know from the first lectures, you can't make a lesser level of measurement into a higher. Only higher levels like ratio or interval can be made into categorical, but not the other way around. So if I said test the hypothesis that younger people own less guns than older people, could be using own gun as the independent variable and age as the dependent variable. Okay, age here and own gun. So this is going to be a t-test. We go to analyze, compare means, independent samples t-test, because whether you own or don't own gun, yes or no, on two independent variables, they don't depend on each other, right? Either you have or you don't. So independent samples t-test. Let me bring that over here. So have gun in home is going to be your grouping variable. Okay. Don't let the wording of the exercise fool you, meaning that okay, younger people, older people, because some of you can mistakenly get age into the grouping variable. And then how do you do age now? You can't define groups because you don't have 1 and 2 in age, but you can put a cutoff point, for example, 45. And then 45 and up are older, and you can call them older, and 45 or younger than 45, you can call them younger. And then you can continue, but that's not the right way to do it. And then what are you going to put in the testing variable? Have gun? No, because have gun is not a numerical variable. Okay, you see, that's a categorical. So it's the other way around. Age is going to be testing, and have gun is going to be controlling. When you define now here, you have 1 and you have 2. Continue. Oh, oops. I already had 1 and 2. Sorry about that. So it's 1 and 2. Why? I'll show you. And then you click OK. Options, what is it? 95%, fine. If you do paste, as you know, that brings the the syntax. So you can just you already copied that code and you can paste it in Word if you want it. For example, oh, Javid, that's you right here. I'm going to create a new document. Sorry about that. Okay, and see the syntax here opened up, and then you can copy this and you can paste it into your Word document. If I ask you to copy and paste the syntax, okay? So that was just a little segue here. But anyway, I'm not going to save these. But we are in the independent samples t-test. Okay. Right, so the age is testing variable. Always numerical variable is the testing variable. Okay, so I hit OK, and now that's what we have. All right, good. This is the way to do it. So, all right, before I go here, because I can't stress this enough, I don't want you guys to lose points in the final. Did you write down what I said about how the question can be phrased? I just feel bad for the people who are not here and they didn't write it down. Hopefully they can watch the lecture. So test the hypothesis that younger people, older people, right, on some sort of other variable that might be, is always a t-test with the numerical variable as a testing variable, right? The number should be the testing variable, like age of respondent. All right, so now we have the group statistic. We have 203 people who have guns at home and 592 who don't have guns at home. See, yes, 203 people, no, 592 people answered yes for 203, and 592 don't. The mean age now, this is a very important thing. The mean age of those who have guns is 54 years old. 45 years old is the mean age of those who don't have guns. So right there, you have an answer to the question. It seems like older people or people who have guns are older than people who don't have guns. By what? By about 9 years. All right. Now, is this 9 years or 8.9 years, this mean difference, significant enough, so that we can confidently say that there is a significant difference? It seems like there is, because the significance is 0.000 in both of these. So now, maybe, Chantel, maybe what, the author of the book in page 343, that's probably what he means when these two are both under 0.05 or over 0.05, then that's what it probably means. So what is this? Oh, wow, look at this. There are 10 numbers, including 3, that have to go behind the decimal point. So it's 0.0000000030923. So that's so small that you can confidently reject the null hypothesis that there is no significant difference. And you can conclude that you have sufficient evidence to accept the alternative hypothesis that there is a significant difference in age between those who have a gun and those who don't. With those who have a gun, n equals 2003. Well, you put in parentheses mean, m equals 54. You don't put the 0.5 because this is age, all right? And the standard error, 1.15, having significant more, being significantly older than those who don't have guns, mean 45, comma, standard error 0.71 or 72. You round it up. Okay, so that's how it is. It looks like, yeah, older people have more guns. It doesn't mean that they have more guns. It just means that people who do have a gun at home are significantly older than those who don't. So it seems like younger people choose not to own a gun than older people who do choose to have a gun. Now, remember that I said that I like these variables so much. What if I did something else? Let me show you. What do younger, older people believe in abortion if woman wants for any reason? How about that? Let's keep age the same and find out. And now change the independent variable into from own a gun to ab any. So let's do the same thing. Independent samples t-test, own a gun, remove it, and get ab any. Now I suspect that 1 and 2 is the same here. Continue, and I'm going to do OK. But I just want to, oops, not this. Ab any, yes, no. So 1, 2, yes, no. Good. Let's look at that. Well, look at that. The mean age is sort of the same. The people who answered yes, that they agree with abortion if a woman wants for any reason, is about 47 years old. But so is those people who don't agree. And look at that. This mean difference here is not significant at all, which means that there is no significant. We conclude that we don't have evidence to say that there is a difference in the mean age of people who answered yes or no, or who want abortion for any reason, if woman wants for any reason. So they are sort of divided. What about if we do some sort of a, if woman is married, for example, or strong chance of serious birth defect? Let's do that. The same 1 and 2 is there to define groups. Maybe I don't foresee any. Oh, look at that. People who actually are in favor of abortion when there is a strong chance of serious defect are older than younger people. And this difference here of almost 4 years seems to be significant. So we look at the first one, 0.01. So yeah, it is significant. And by the way, up here, we looked at 0.716 because this p-value for Levene's test shows that there are no unequal variances. So that's the bottom number. Here is the top number because this significance of the Levene's test is large, greater than 0.05. All right, so you can play around with this. I want one more thing. I want to figure out in the gun ownership again. But now I want the gun law, whether they favor or oppose gun permits. Now, favor gun permit is less favor or the opposing gun ownership outright. So you want more permits. So let's do this. Gun law. I want to figure out in the gun law who opposes or favors gun permits in terms of age. So let's look at that. Age, where is age? Age of respondent is right here. I already have it. And gun permit. Let's look at that. Not have gun. No. Where was it? Gun permit. Gun law, right here. It should be 1 and 2 again. So let's look at that. Oh, it doesn't seem like there is a difference. So age doesn't make any difference whether or not one favors or opposes gun permits. Okay. How do we know? First of all, we eyeball this. But if you look at that, there are more people who favor gun permits. So it means that there are more people who oppose having a gun outright. You need to go through a permit. But there are about 144 people who oppose gun permits. Now, this 0.5, half a year of age difference, doesn't seem like there is a significant age difference because we look at the top row, so it's 0.748. That means that there is a we retain the null hypothesis, we don't reject it, therefore we don't accept the alternative hypothesis that there is a significant difference. Okay, one more thing here. I wanted to look at, okay, gun laws and respondents' income. Let's see who favors gun permits more, those who have more money or those who have less money. So, independent samples t-test again. Now, I don't want age. I want to look at, so another way to ask this question is test the hypothesis whether rich or poor, in these kind of terms, rough terms, favor gun permits more. Okay, so if somebody doesn't really understand the t-test, we'll go and create a variable from the income in dollars to sort of separate those who are rich and those who are poor. But that cutoff point only be arbitrary, so don't do that. Respondent's income in constant dollars, so that's the test variable. Gun law 1 and 2 remains the same. Okay, so I want to test that at 5% alpha level. Click OK. All right, look at that. It seems that those who favor a gun permit, or sort of oppose owning a gun outright, make more money than those who oppose gun permits or favor just having guns by almost $12,000. No, $11,500. So this is, those who have more money want the permit more than those who have less money. That's what it means. Now, is this $11,450 significant enough to show that rich or poor or whatever? You can't really say that the mean age of those who oppose it are poor, but you have to go to the independent samples t-test table, look at the Levine's test. This is greater than 0.05, therefore you look at the top line. Now, here's where another statistician could come in and say, why do you compare this 0.09 against 0.05 alpha level? What if you had an alpha level of 0.1? In that case, this significance p-value is going to say that we don't assume equal variances, we assume unequal variances. So we look at the bottom row. In this case, it happens that both significant values here are greater than 0.05. So in this case, whether you want to look at the top row or bottom row, it doesn't matter. But it goes to show that even for the Levine's test, you have to set up a reference probability. You have to set it up right at the top. So I would suggest that anytime you have a t-test, you select an alpha level for the t-test and also for the Levine's test, f-test. So you'd be way better off if you selected 0.05 and alpha of 0.05 for both. Okay, so keep that in mind too. I really like this example. I didn't mean to show this because I didn't know what the result would be, but it's a good example of what this means. 0.09 greater than 0.05, but smaller than 0.1, right? That's a great example. Okay, in this case, it means that this mean difference is not really significant. So even though you have those who favor gun permits make more money on average than those who oppose gun permits, this difference is not significant. That's what it means. Well, generally, my gut feeling in the beginning said that, okay, those who make more money actually would oppose gun permits, because if they make more money, they would probably want to sort of defend themselves more. I just, my hypothesis was not correct. It seems, right, statistically. And you would go to 95% confidence level. You see that the lower and upper limits are of opposite signs. So this means that this difference could be negative too, but it could be positive as well. So if it's negative, that would mean that the opposed group would probably, in 95% of the cases, would show that is also greater than those who favor it. So that's why this difference is not significant. Yeah. Well, although my hypothesis, when you eyeball it, is not correct, statistically, my hypothesis stands. All right, good. Well, the null hypothesis stands, and if that stands, the original is not accepted. Well, all right. There's so many more to do here. I suggest you go and do it on your own. It's really great, and you learn some things. All right, I want to move on to ANOVA now, and then we can also talk about ANOVA next week, because now we have only half an hour. We can spend so much in ANOVA and t-test alone, but so theoretically speaking, ANOVA is a distant cousin of t-test. The only difference here is that ANOVA has 3 groups that you have to sort of test the difference. T-test had 2 groups, ANOVA has 3 groups. That's the only difference. If you want to really learn ANOVA, I would suggest, let me just close that you look at my video here. I know it's 30 minutes long, and who has 30 minutes to spend, right? But when in the age of Twitter and Facebook and Instagram, or Netflix for that matter. But I would really suggest that you go and check this out, because I have taken the time to talk about the theory of ANOVA, how all of this comes together.